Thank you. It's a great pleasure to do this and to have such a broad audience, you know, to present my my work to. And I'm actually very much looking forward to any types of questions that can come out of this. You know, also if there's more fundamental questions, I'd be happy to answer emails later or anything that could come up. So that said, let's just get right into it and let's get started. And I'm going to present distributional synthetic controls. And as you can see, it is a version of synthetic controls. In particular, I will argue that it is a natural notion of a regression of outcomes in a pretty general space, which is based on the classical idea of synthetic controls. And the distributional part is going to be the novelty in my talk. Okay, so let's just jump right in here. I think at this point, many people are aware of this picture. It's a very fundamental picture. It's one of the main applications of the synthetic controls, or one of the main examples, early examples of the synthetic controls method, of the classical synthetic controls method. And I also use it to just explain the very basics again. So imagine if we have an aggregate unit that could be, for instance, a state in the United States that at some point undergoes a policy change, a strict policy change. In this case, it is the passage of Proposition 99, and our state of interest is the state of California. And we as researchers, we are interested in some aggregate outcome for the classical method. And the aggregate outcome in this case is per capita cigarette sales in packs. And we observe a time series of these sales over time. And we want to figure out what the causal effect of this policy change is on our aggregate outcome in that state. And in general, you could just argue, okay, I just take everything that's in a post-treatment period, which is here, and I subtract from that everything in the pre-treatment period, and that could be a treatment effect. This requires very strong assumptions to give you a correct effect. In particular, it requires that there is the only effect on our outcome is through our policy change, which is highly unlikely in economics and in many other settings. And as you can already see here, the outcome has a specific trend already. And so what you would want to do is you want a control unit, a unit that has a very similar trend in this variable you're interested in, but did not receive the actual treatment of interest at that point. Now, this fundamental idea of synthetic controls is to see that in many cases, there is not one good control unit, and like one unit that has a very similar trend, and also from like other covariates is similar to our treatment of interest. And that's why this fundamental idea of the synthetic controls method comes in. And it actually says that, well, there's not one good control unit, but a weighted average of those control units, potential control units, could be a good control unit overall, this synthetic unit that we construct as a weighted average. And as you can see here, the synthetic California was constructed as a weighted average of other states in the United States, and it actually manages to trace out these, you know, the path of the outcome of interest pretty well up to the actual treatment. And all of this causal inference idea is based on this idea of matching on observables, meaning that, okay, if the observables follow a very similar trend, then we argue that all of the unobservables that influence our different states are similar in all the states, so that our control unit really captures everything that is not related to our treatment. So that is the actual classical method. And now we go into a little bit more of a first theoretical step, because this will be the mathematical idea that I will generalize. And so we have T time periods in our picture. That's from 1970 to 2000. We have pre-intervention or pre-treatment periods, T naught, and using the classical now notation, we have from j equal 2 to j plus 1 control units, and j equal 1 is our target. So j1 would be California, and we observe in the classical method some aggregate outcome. This could be a vector or a number, some average. And then the synthetic controls method proceeds in 2 steps. And usually in the first step, and this is the interesting step, at least in my book, in the first step, you want to find the optimal weights of your synthetic control estimator. The weight in this weighted average of your potential control units here that replicates as close as possible your target. Okay, so you want to find the weights that minimize the distance to your target of this average of your outcome. And currently, I'm just using the standard Euclidean norm, but you could use a weighted norm and anything you want. Okay, so this has some of a flavor of a regression on outcomes, right? Because we only consider outcome variables here. And then you do that at each time period. At each time period, you get optimal weights. And one way to do to obtain a complete weight over all pre-intervention time periods is to just take another potentially weighted average of your weights you have. And then in the second stage, because this is where you don't observe the counterfactual anymore, right? Because your counterfactual is what would have happened to California had it not passed had it not passed Proposition 99. So you don't observe this. And in this sense, you make this identifying assumption and say, okay, well, the weights are still going to be optimal. Those are still going to be the right weights in the post-treatment period. And I can use those weights to create in the post-treatment period my synthetic California. And then these differences will give me the average treatment effect or the causal effect I'm interested in. Okay, so these are these 2 steps. And in particular, the first step is this interesting step that I will generalize and I will show provides a very natural and novel notion in the mathematical literature on regression on functional spaces. So what I'm going to do today, since this talk is called Distributional Synthetic Controls, is I will just see what happens if I replace an aggregate outcome by some functional property, by some functional quantity. And the most natural one to deal with this is to look at the law, at the probability distribution corresponding to the specific random variable. So I will look directly at the probability distributions and not just as at aggregate outcomes. And suddenly we'll have a functional property here. And then the first question to ask is, well, this is a generalization. Why is this useful? The first, and this is more of an abstract answer, is that this provides a segue into causal inference using functional data. So you can have pictures here that can be described as a measure. You can have speech data. You can have specific types of network data. You can have a much more general set of potential high-dimensional data that you can use this very, very neat and very ingenious method of synthetic controls on. So that is the first thing. It kind of generalizes the whole setting to a much broader spectrum. And the second one, and this is more mathematical, is that as I said, it gives you a natural definition of a linear regression of outcomes for now, because synthetic controls is like a regression on outcomes on probability spaces. So meaning we can now regress probability measures on each other directly. And why is that useful? I just give you some abstract example. A regression of images. These are simple images, but they could be brain scans. They could be maps where you have trading routes and shipping routes and many things. And you could regress different shipping routes at different times onto each other and try to explain a specific shipping route or a specific thing you see by some other shipping routes. Okay? Here we have a very, very similar thing. Simple setting. We have specific control images, right? I just picked some images, and these could be your control states, right? This could be Colorado, Washington, and so on and so forth. And then you have your target image, which I deliberately chose a little bit different than my control images, because this is where the synthetic controls method shines, right? To get a combination of elements that don't really look like the thing you want to replicate, but a combination of those can replicate this well. And this is the whole idea. So this could be your California here, like a picture of California, imagine that. And then I propose a method that is what I call geometrically faithful, for lack of a better word, in the sense that it actually manages to replicate the whole geometry of what you want. So the whole functional thing you want. In a picture here, as you can see, it really tries to replicate this white little dot, even though I put in these squares on the fringe. And you can already see that none of these control groups are actually a good control group for my target image. But the thing I propose does a really, really good job. And this blurry part is just because I use a very efficient way of estimating it. If I choose something that is takes much longer to estimate, but would also work, the actual blurry part would go away, and I would be able to replicate this almost perfectly. Okay, so this is only due to me using a very simple way of implementing this, which is also a very fast way. So then the next question you might have is, okay, now we use probability measures, and there's a million things I know about these things, and I know that I can take mixtures of probability measures. So why don't we just use simple linear mixtures of probability measures? And the reason for why this doesn't work, or for why I argue this doesn't work, is that linear mixtures in this setting don't have this notion of geometrically faithful, as you can see here, because linear mixtures depend on the supports of the distribution they essentially choose from. You can, to make this a little bit clearer, you can see this here. You have your 4 control groups, and all of these white squares are essentially the support of your distribution. So your distribution is just supported on these white points. And then if you take a standard simple linear mixture, which we all know, and it should be a convex mixture, because you cannot have your lambdas outside the unit simplex. By the way, the unit simplex is a convex set such that all of the weights are non-negative and sum up to 1. And if you do that with the simple mixture, you will get out a probability measure. But for instance, you cannot generalize in general the simple linear mixture to allow for weights that are negative, because then you won't in general even get a probability measure out of it. And the issue is that mixtures rely on the supports they are given. They cannot change the support essentially. But what I propose is something that will change the support to what you want, right? And this is this geometrically faithful type of idea that I introduced, for lack of a better word. But the idea should be simple. The actual concept should be simple. We want to find the weights that minimize a certain distance, you know, Kullback-Leibler, any type of distance you can come up with, the L2 and so on, the distance of my weighted average of my controlled distributions to my target. That is the fundamental notion that I will also use. And then in the second stage, I assume that my weights still stay optimal, and I just find an average. And as you can see here, this really does not do what we want it to do. The whole point of synthetic controls is to replicate what you want, to replicate your target, which is not possible here. Okay. So what do I introduce? I introduce a version of this, but in a different space of probability measures. And the space is the 2 Wasserstein space of square integrable probability measures. And this will be my 40-second or 1-minute introduction to the Wasserstein space. And I hope I'll do a good job. We'll see how that goes. So the main idea is this Wasserstein distance is a distance on probability measures, which is derived from the underlying space that the probability measures are defined on the underlying support. So to make this a little bit clearer, in 1781, Gaspar Monge posed a specific problem where he said, okay, I have a pile of dirt and I have a hole of the same volume, and I want to figure out the most efficient way of putting this pile of dirt into the hole, right? And most efficient way, you need to use a specific type of cost function for that. You want to minimize a cost function. And the two-Wasserstein space as a cost function uses the Euclidean norm, the underlying Euclidean norm. Okay, and as you can see here in this little picture, that just means it just shows this graph here is the optimal transport map. It basically shows which point in the distribution, in the blue distribution, gets mapped to which point in the red distribution, right? And you go through this. And in order to minimize the Euclidean distance, you obviously, or not obviously, but you will in general find an optimal transport map that goes from the top left to the bottom right, because points that are pretty close together, it's not hard to actually transport them, right? And what you would want is to minimize the average of this transportation cost for each particle. So that was 1781. And it became clear pretty soon that the Monge problem is not always satisfied, meaning that you won't always be able to have a function that tells you for which point goes to which point. Sometimes you need something more general, where it can happen that you have a specific point in the blue distribution that will get mapped to 2 points in the red distribution. Okay, and then you would have a transport plan, a correspondence essentially, and you would have some horizontal elements here, which is no longer a function. And Leonid Kantorovich in the 1940s realized that and said, okay, I propose a new problem for this optimal transport problem, which is a convex relaxation of the Monge problem. So instead of just trying to find a map, I just try to find a joint probability distribution. So this capital pi here, which is a coupling, meaning that it is a joint probability distribution such that P of X and P of Y are its marginals. Okay, sometimes you can think of this also as like a general copula, if you will. And this will be your transport plan, and in particular, it will allow for correspondences. So the support of this probability measure will be a correspondence and not necessarily a function. Okay, so this is important because later on I will show when my method works and when it doesn't. One particular thing is that as soon as your origin distribution, the blue distribution, is absolutely continuous, the Monge problem always has a solution, and you can show that both problems coincide. Okay, and the value function of this problem is your Wasserstein distance, and it defines a distance on the probability measures based on the underlying space. Okay, and since it does that based on the underlying space, it introduces a lot of geometric information into the problem. So you can, in contrast to mixtures, where mixtures are just they don't take into account the underlying support. You assume, for instance, with the Kullback-Leibler distance, you want that the two distributions have the same support essentially. Here, the distributions can have very, very different supports. So they can be very, very different. As you can see here, this distribution doesn't have a support from 60 on, but this distribution has a support until like 90 roughly. So they have very different supports, and you will still get something non-trivial. That is one very, very useful property, in particular because I want to replicate something that might have a completely different support. And that is why I use the Wasserstein distance. Okay. So far, so good. Now I'm going to introduce one more concept, and then I'll pause for questions. So something that I will also need to use is a notion of average on my Wasserstein space, right? Because that is the whole idea. I want to find some form of mixture of my probability distributions. And as I argued, the classical mixture doesn't give you what you want. So you would want something that is not bound to the support of the donor distributions. You would want something a little bit freer. And barycenters in Wasserstein space actually provide that. And they were introduced in 2011 by Abadie and Guillaume Carlier. And Carlier is a co-author of Alfred Galichon. And he also, with Ivar Ekeland, I think 2 or 3 years earlier, published a paper on optimal transportation and teams, where they introduced a very general way of barycenters in Wasserstein space, but much more general than here. And this was published in Econometric Theory. And then Martial Aguier and Guillaume Carlier published in 2011, a little bit later, a more specific problem, right? Only for the 2 Wasserstein distance. And that blew up and is now a seminal paper in the mathematical literature here. So what is this Wasserstein space? I could have also put up a picture of Maurice Fréchet, because these are called Fréchet means. These are the natural generalizations of a linear average to a nonlinear space. So what you want to do is to find a barycenter, an average for a given set of weights, which minimizes the specific distance or squared distance to each of these boundary points, essentially, or to each of your donor points, and that will give you the average. So you minimize the distance, and in fact, this is a classical generalization and a very natural generalization of the linear average, because you can also show that you can write the simple linear average, this thing here, the simple linear average. You can write this also as the element that minimizes the squared Euclidean distance to all of the donor distributions, or the donor points, essentially. The nice thing about this is that this is generalizable to probability spaces, for instance, and this also works if your lambda is not contained in the unit simplex. So if you have negative weights, and then your barycenter will essentially lie outside, and you will have something like extrapolation, which is the same thing as the classical synthetic controls methods does. So this is why I think using the Wasserstein space is the most natural. One last thing, here's a simple example. I sampled 4 Gaussians with the same small variance and just different means. And then I show what the mixture distribution is, and it is obviously supported on the supports of the original 4 distributions, and is in particular multimodal. And the Wasserstein barycenter is exactly what you would want. It's geometrically faithful in the sense that it is a normal distribution with the average of the averages and the same variance. And this is where I can pause for some questions if there are any.
Yeah, so I think there's a question from Jesse Shapiro. Jesse.
Hi, can you guys hear me?
Yes.
Okay. Hi, Florian. Greetings from your friends in Providence.
Hi, Jesse.
Hi. So I wanted to step back and understand a little better the economic motivation for going in this direction. So like in the Proposition 99 example, what would be the policy motivation for being interested in moments of the distribution of an aggregate like per capita cigarette sales beyond the first moment?
I see what you mean. Yes. So you could be interested in the whole distribution. So maybe this per capita cigarette sales, if you don't want to have the average, but if you want to see a distribution over the population in California, for instance. Another example, I currently have a student working on a similar problem, and this is about minimum wage implementation and how it affects the stock market, essentially, or stocks. What you can do with my approach, or with this approach, is to look at an aggregate level and look at sectors, for instance, and see how a change in the minimum wage affected the stock, not just on average, like an aggregate number, but affected the lower percentile, the upper percentile of companies, depending on their returns and so on. And in a more, non-time series setting, you could probably look at the whole distribution of household income. Sometimes it could be interesting to not just have an average of household income, but you would want to see, okay, what happens to the whole distribution? How changes the whole distribution over time? And this is something you could answer with that.
So to clarify, in this case, like in the Prop 99 case, it wouldn't be that we would be looking at the distribution of per capita cigarette sales, that is the aggregate, but rather the distribution of cigarette sales across, say, the population of each state.
For instance, yes, this is what you could be doing here. And the thing is, my thing gives you one weight for the whole distribution. So you're not mapping specific quantiles, and you're not matching specific quantiles with different weights, but you're matching the whole distribution with one weight. That is the whole thing. But yeah, thank you.
Thanks.
Thanks, Jesse. So there was one other question from the audience. Let me just ask that from Andre Schracker. Does this also work for discrete distributions?
Yes, this is going to be very interesting. Thank you for that question. Yes, it works for completely discrete distributions. The computational part will be very hard. And I will show that this method is currently, as I show it, theoretically very easy, but practically super hard to do. And my main contribution is a very efficient way of doing this in like a regression framework. And you can do regressions on univariate and bivariate and trivariate outcomes in seconds, almost instantaneously. And in that case, it only works for specific discrete distributions, namely for those where the Monge problem has a solution. And that holds for many, many matching problems in economics, where you have the same number of elements on one side and on the other. It will always hold for that. It holds as soon as your target, as California is continuous, even if you have other discrete controls. And it holds in many, many other discrete settings, but not in all settings, because there are settings when the Monge problem doesn't have a solution and the Kantorovich problem has. And in that case, you cannot use my simple efficient estimator. And in that case, it's not even clear if you get a consistent estimator. Okay, so it does work in many cases, but not in all.
Thanks. Any other questions? I just want to also give the panel an opportunity to ask any questions.
So I have one question related to the first question that was asked. Suppose you are interested in a particular functional of your distribution. Do you think you can incorporate information of that particular functional in your optimization problem? So can you adapt the type of metric with respect to the functional that you are interested in, say, I don't know, the Gini index, or as I was saying, the effect on the median and so on?
That's a great question. So yes, so first of all, I currently have distributions here, and this approach works for probability measures that are between 0 and 1. If you have a functional and you map, if you actually mean functional in the sense of a functional that maps to like R again, and you have a point, you can use my thing and then apply the actual functional afterwards. If you have an operator where you take in something that is a distribution and you get something out that is also not finite dimensional, you know, like a specific Gini transformation or something, then you can adjust my approach to this. But if this new thing that comes out is not between 0 and 1, like a probability distribution, I will have to generalize my approach. And I'm actually currently working on this with some co-authors, and to make this approach also applicable in settings where you have distributions. Let's say household income, and you don't care about relative household income. Currently, I can deal with relative household income because all states, California and so on, need to be normalized. The distribution needs to be normalized between 0 and 1. If you want something absolute, if you want to match something absolute, then the distribution of income in California will most likely be higher than the distribution of income in Nebraska, let's say, in an absolute sense. And then you're not matching distributions anymore, but something more general. And I'm currently working on generalizing this. And this would also answer Davide's very good question.
All right, let's keep going, Florian.
Okay. Yeah, thank you. So the second idea to generalize the classical synthetic controls estimator then is like, okay, I just do it in the most naive way, meaning that I want to find my optimal weights that minimize the distance, here the Wasserstein distance, of my average, the optimal average to my target. The problem here is, as you can already see, this is not a simple problem to solve anymore, because just computing the average is incredibly complicated, right? You have to first solve a minimization problem and then plug that into another minimization problem. So it's a bi-level optimization problem, which is very hard to solve. And in particular, there's one other paper in the mathematical literature by Bonnell, Couturi, and Perret they use this exactly this type of argument for transporting colors between pictures. So you have a specific landscape of a specific color that's during the day, and you want to see what this would look like at night. And then you have a bunch of other control pictures at night from like many, many different scenes, and you want to find a combination that replicates something closely, right? They use this approach. They try to solve this optimization problem, or they do solve it, but only for histograms, because when you have pictures, you can essentially look at this as a discretized distribution, right? For small histograms in the binary case. And they also don't really care about the optimal weights. They just want to find some combination of colors that gives you something nice. In causal inference, we really, really care about the optimal weights, because the weights are those that will give us our counterfactual afterwards. So having unique weights is very important to us. And you can actually show, and this is what the authors there acknowledge too, that if you try to solve this bilevel program directly, and they do this with like a very nice gradient descent approach, they can only find a stationary point, meaning they don't have a global minimum in general. They just find some optimum and say, okay, this is all we need. And it is all they need for their specific setting. But in the causal inference setting and in econometrics, where you care about the models and the inner workings, those weights are the thing we're actually after. And we would want something that gives us unique weights and a global minimum. So solving this theoretically, yes, is nice, but won't even give you a consistent estimator for your lambda, because this optimization problem is so complicated. Okay, so this is a naive first approach, and it doesn't really work. So what I propose, and this is the main contribution of the whole thing, is I propose a very efficient way of solving this problem and getting a unique set of weights in many settings. And to explain this briefly, as a starting point, I need to talk about barycenters and also something which is called a deformable template. I realized that my idea is actually very closely related to the concept of a deformable template in pattern recognition, where you have a specific image and you want to deform that image to look like other images. Like you have a fish and then you have a duck, and you want to see how you can deform that fish into a duck. This is what they do in a specific sense for deformable templates. But the idea here is that I use this characterization of my barycenter, meaning that instead of solving this complicated problem for my barycenter, Agee and Carlier showed that the barycenter for given lambdas, for fixed lambdas, is defined by this simple equation, meaning that this is essentially the average of the optimal transport maps. The weighted average for the given weights of the optimal transport maps needs to be equal to the identity. And you can actually prove this. So intuitively, very intuitively, what this new formulation means is that you want to find a balance for your given weights. You want to be such that this average of your transport maps, your optimal transport maps, which were those, of your optimal transport maps is balanced. So they're actually close to the identity, and you can formally prove that. The problem with this is that this defines the barycenter, and it wouldn't help me because you would need to know lambda for this, and I don't know what lambda is. So what my idea is, okay, why don't I use the optimal transport maps, not with respect to something I don't know, the barycenter, but with respect to the actual target I'm interested in. And now this becomes this classical definition of a deformable template. So these optimal transport maps now are optimal transport maps between something you see, between your target, California, or the distribution of household in California, and other states, Colorado, Nebraska, and so on. And you can compute those, okay? And since you want your lambdas, you just compute those optimal transport maps once. And there's very efficient ways of doing this currently. They came out last year, essentially. And then you just run a linear regression. You just run a linear regression. And the intuitive idea is now, instead of finding instead of finding a barycenter that is as close as possible to your target, you want to make the target, you want to find weights that make your target as close as possible to some barycenter. And this notion, this like reverse way of thinking, I realized is the same idea as having a deformable template from pattern recognition, but only in a Wasserstein space and a little bit more general than just for images. So that is the idea. We want to make our target as close as possible to a barycenter. And this works if the target lies in this lies in the convex hull, or it doesn't. It works in any case when there is a when the Monge problem has a solution, and that is the nice thing. So intuitively, and after this slide, I will stop again for questions. Intuitively, my approach is now this. I use this idea of I use this equation here, and I just take an L2 norm, because due to statistics, right, you will never be able to have perfect equality here. So you minimize some form of L2 norm. And I presented that at some point internally to a research group of mathematicians, and one person pointed out that it is useful to do this with respect to the L2 norm of your target. Before, I had just the L2 norm with respect to Lebesgue measure, which works perfectly well too. But if you do that with respect to your target, suddenly I have another level of mathematical justification for my approach. Because what I do essentially by doing this is I don't work on my Wasserstein space, which again, I write this as a sphere, and I plot this as a sphere because you can show that the Wasserstein space in general looks like an infinite dimensional sphere. So projections need not be unique there, and it's kind of really messy to actually work on this. But by using my approach, I'm actually working in the tangent space, which is linear in the tangent space of my target. So essentially what I do by doing this, I look at something linear, and then I just want to make my target as close as possible to my control units in the tangent space. And this is why everything I do is so very efficient, because I don't have to deal with like non-linear things. Everything is linear, and I have a linear regression. Okay, so this simple line now will give me my optimal weights. And I will show you in like a second that in the univariate case, this is instantaneous. Even if J is hundreds and thousands of control units, this is instantaneous on a MacBook. Like, you don't have to do anything. And in higher dimensions, it's close to instantaneous. And if you go to very high dimensions, then you need some neural network implementation and so on, and it takes longer time. But for most applied intents and purposes, this is as quick as running a linear regression. Okay, and then you have your optimal weights in your first pre-intervention stages. You want to use those optimal weights in the post-intervention stages. And for this, you simply compute the barycenter. And there are many efficient ways of computing a barycenter, not just one specific way, but there's a bunch of optimization routines that actually do this very efficiently. Okay, so the nice takeaway, and this is the main contribution of this, mathematical main contribution of this paper, is that I have a simple linear regression, or a simple convex valued regression if you want your lambdas to be non-negative and sum to 1. No bilevel program. It has a global minimum. I show in the paper that I have consistency towards the weights and also consistency towards my counterfactual. And it works as soon as the target is absolutely continuous, even if my controls are not. But it also works in many cases, for instance, for matching cases, as I will show later, when the target is discrete. And this is where I just pause again for some more questions.
All right, thanks, Florian. I don't think we actually have any questions from the audience at the moment, but Davide or Alberto, do you guys have any questions?
I do have a question. So in the usual synthetic control, there is by the way, this is so cool, and thank you so much for the talk. But in the usual synthetic control, there is this notion of fit, right? Like when you're done, like you look at the characteristics of the synthetic control, you look at the characteristics of the treated unit, and you go and see whether they match. one by one, right? And is there a similar notion here, like apart from, you know, applying the Wasserstein distance? And that's like, are we, you know, we have any sense in which we think that we are doing well, or perhaps it's not a good set of donor units or something like that? Yes, thank you.
Yes, that's a wonderful question, Alberto. And currently I'm eyeballing. So my current answer is to eyeball, because you can't compute, obviously, you can't compute the actual distance between the average you obtain for those weights and your target. But this will be a Wasserstein distance, and it doesn't really tell you anything. The Wasserstein distance depends on the underlying space. It can be very large or very, 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 very small. So very large values of the Wasserstein distance for specific problems will still be a very good fit. I have been thinking about this and currently making sure that this works well. In the univariate case, it is obvious. It is obvious to do this. You could do a Kolmogorov-Smirnov test and see how close you are. This is well established. You could do something like this very, very closely. But in a true multivariate setting, which I will show later, in a true multivariate setting, I don't have a good answer except for eyeball. Well, no, actually not true. Thank you. Actually not true. I just realized that. You have a good way of looking at this, and it's this linear regression. If you are close to the identity, and you can check that at every point. If you are close to the identity, this does not depend on any units. This does not depend on any units. This is just the identity on your underlying space. If you are close to the identity, then you have a good thing. I don't have a full measure, like how close do you have to be to do it well, or to be a good, synthetic controls. But I also think that it kind of depends on, if people are happy with this. For instance, in this multivariate setting that I will show later, this is what I get in my synthetic controls method. But you can see here that my optimal transport maps, they almost all disappear, which means that they're almost all exactly equal to the identity, especially here in the center. And I think there's a way in which you can make this formal and actually come up with an actual test. That's a very good question. Thank you. And this is a perfect segue into just showing you the applications. And it works very well. This is just promoting this because I really think this works fantastically well, and it's instantaneous. And I will show you some nice ideas here. So I just had a target distribution that I sampled as a mixture of 4 normal distributions randomly, like a random mixture of 4 normal distributions. This is my my black line. And then I have some controlled distributions, which are the 3 gray dotted lines. And those are mixtures of 3 normal distributions, because I figured, they will probably have a hard time replicating the mixture of 4 normals. To make it a little bit, harder and see how well my my DSC behaves. And here I only allow for interpolation, that my weights are in the unit simplex. And you can see I get something which is really close. But since my controls are so different, essentially so different, quote unquote, in this univariate sense to my target, I don't really do a good job here. If I add another distribution, now I have a set of 4 controlled distributions. And they are placed in like a nice way. And again, they are placed randomly. This is not cherry picked. I just picked the 4th one and it turned out to be the one I need. Then you can see that it replicates the stuff reasonably well. But this is interpolation. So I still use the information from a mixture of 3 normals to replicate a mixture of 4 normals. So there are some issues here that I cannot replicate well, even if I have hundreds. And again, simulating, running my thing and plotting this picture took 1.5 seconds. So this is instantaneous. And these are 100 controlled distributions, but you still see that I use the information of my mixture of 3 normals to replicate a mixture of 4 normals. Here, these maps, how much time do I have? I have 12 minutes left. Okay, that's actually pretty good. For these maps, I want to show how closely I can replicate this. And this is an answer to Alberto's point, in the sense that, well, how good is my control distribution actually? And here you can see that in the upper parts, if I have those 3 three guys, as you can see here, in the upper parts, my control units do really well, or my synthetic control unit does really well, but in the lower parts, it doesn't. And then it's very easy to come up with like an actual distance and a test potentially, but I have not thought about this. So currently this is just eyeballing. Okay, but it should be straightforward to come up with a nice test for this. And as you can see, if I add one more, you see that sometimes I have like issues with those 4 mixtures. Sometimes because I only have mixtures of 3 normals, it has a little bit of issues. But this is one way to check how well your method performs. Like how well are my optimal, or is my average of my optimal transport maps replicating the identity? And the same thing holds for 100. This is very interesting. This is very interesting because it goes into more of a philosophical mathematical question here. The weights can be negative, right? Sometimes you want to extrapolate, just like in the synthetic controls method or many other methods, you want to actually have a linear regression sometimes. You don't just want interpolation using the information given, but you want to extrapolate to settings that you don't observe. And very, very interestingly, this is what I wanted to show. It works really well. This is the exact same problem as here, where these are my 3 controls and the same target. So the same as before, but now I allow for negative weights. And you can see it does much, much better up until the point where one of the distributions doesn't have a support anymore. So this distribution is 0 here. And then extrapolating outside of the support obviously gives you something unstable. And this is a connection to the propensity score method that you need supports to overlap and so on. But we only need that. We only need that in the extrapolation case. In the extrapolation case, we never need that if we just use the information we have. Then we can be far off, but we always use the information we have. If we want to extrapolate, we can only extrapolate up until where we have all elements the same support essentially. And here too, you see these instabilities, but it does a much better way of replicating than before, especially here, as you can see. Okay, and now I also allow for negative weights, but I do it in the same sense as the synthetic controls estimator. The weights still have to sum to 1 because that gives this natural analog of a linear regression, as the 2015 paper by Abadie, Diamond, and Heinmüller shows. And then I also want to show this in a continuous bivariate case. So I have different copulas here. I think this is a Frank, this is a Clayton, and this is another one, or Clayton Frank, something like that. So these are 3 different copulas because it's very easy to deal with this with the setting. And my target is just a uniform, you know, an independence copula. And this one looks very, very different from those copulas. But you can see that my method really tries hard to replicate this guy. It really tries hard to replicate this guy. And as I said, these are my optimal transport maps. These are my optimal transport maps. And you can see how the mass shifts from my target when transporting from my target to my control units, how it shifts the mass. And then if I take this optimal weighted average, you can see that I'm actually pretty close to the identity. And drawing all of these took less than 30 seconds. So it's very, very quick because of my linear regression approach, essentially. And here is the most important part, and then I'll stop after this and pause for more questions. I try to do this in 1 minute. This is a purely discrete setting. So I have a purely discrete target, and I have matching control groups. And I need the same, or I need my target to have at least as many points as my control groups. And then, because then the Monge problem has an optimal solution, has a solution. As you can see, each point in my control gets matched with 1 point in my target. I don't have to split mass to 2 points, right? This is one example that is purely discrete, where my super efficient approach works. And again, this takes mere seconds to compute. And as you can see here, we just take the optimal transport maps from my target to my respective control groups. And if I run my simple program, you can see that this is my replication of my target. So my control groups here do a reasonably good job of replicating my target. In the discrete case, there's nothing continuous here, fully discrete. and it's bivariate. It's not just a simple univariate case, right? These could be shipping routes, for instance. These could be shipping routes and or optimal transportation ways in the L2 distance in this case. Like what is the closest distance from a factory to a specific store, and you match those, and then you want to replicate something here. So you could use this as an example, for instance. So we have this, and here I say that my target is very, very close to the convex hull. So my target is very, very close to here, and it is therefore easy to replicate it via interpolation, because I only allow for interpolation weights. Here I have an example where I deliberately chose my target to lie far away from my control units. And you can see here that this is the best I can do with replicating it by allowing for non-negative weights that sum to 1. So for interpolation. And that gives you a very neat intuition of what in this discrete setting this convex hull of these distributions would look like, right? Because I'm pretty far away from my convex hull here. But yeah, this is these are some things I wanted to show. And now for the last 5 minutes, I want to talk about identification, and I'll stop for questions before that.
So maybe just a quick question. Do you see that you may lose some information by matching based on the Wasserstein metric with respect to, say, matching based on the means if you actually just target the average effect? So if you have a specific target of your distribution.
That's a good question, and there's 2 answers to this. The first one is, if you only care about an aggregate number, classical synthetic controls is perfectly fine. If you care about the distribution and want to compute something after that, for instance, like an average after that, you will probably get something slightly different if you use my Wasserstein. Maybe. In practice, maybe, but theoretically, you should not. But because the idea is, for my Wasserstein setting, I use 1 weight to replicate a whole distribution, right? I get 1 weight for each distribution. Whereas if you really just care about aggregate outcomes, like averages, you just need 1 weight for a number. So if you just care about aggregate numbers, then in that case, classical synthetic controls is the actual way to go. You can use my method first and then compute an average, but that is just going like 2 different routes instead of going there directly. However, if you want many specific different elements, aggregate elements, like an average, specific quantiles, distributional effects where you subtract one distribution from the other, and so on, then you would use my stuff. And the only loss I can actually think of is by allowing for or by requiring that I only have 1 weight for the whole functional thing, for the whole distribution. I'm not just trying to replicate each point in a distribution with its own weight. That's a very good question. So in that case, I do lose a little bit, but it's like a philosophical thing. It's not because of my method, but it's because I want to replicate a functional thing with 1 element, with 1 number, which is a weight. But yeah, that's a very good point. Okay, if there's no more questions, then I'll
keep going, and then we can move to
perfect
questions.
Yes. So in the last 2 minutes or 3 minutes of this talk, I'll just I'll show you a kind of new result, I think, that shows when any type of synthetic controls method is applicable, also my method, this more functional thing. And for this, I use the same model as the changes and changes estimator, because in the univariate setting, where the changes and changes estimator is applicable, my synthetic controls method is like the same complementary approach as the classical synthetic controls method is to the classical difference in differences estimator. Right. So once you take an average and in a difference in differences, you have a control group and compare the control group over time. And my approach in the univariate setting has the same idea and is related exactly the same to the changes in changes estimator as the classical synthetic controls method is to the difference in differences estimator. So that's why I wanted to use the changes in changes model, the model from the changes in changes estimator, which is a non-separable model. We don't know what this function h is, and we don't know what our unobservables are, and we allow this function to actually change over time. And there are two specific settings. One is repeated cross sections, where we say, okay, we don't have that long of a time span, so probably the unobservables won't change too much. That's why the unobservables are not indexed by t. And then we have longitudinal or panel data, where it's a longer time frame and where the unobservables probably also change with over time. So this is this classical model, and the idea is that any outcome for any unit that is not treated, which means all of my control units and also my treated unit had it not received the treatment, which is my counterfactual, they all have this type of model. And the question is, what type of function can we allow for in order for my method to produce the correct counterfactual? And this will clearly relate to the weights here. And the idea is very, very simple. And this is the last thing I'm going to say. The idea is very simple because we have an extrapolation step over time. 2 time periods are essentially enough for my approach too. Meaning that if we have one pretreatment period, what any synthetic controls estimator does is they find a weighted average of my control units that replicates as closely as possible my treatment units. And then after the treatment happened, we still assume that the weights are optimal. So we have an extrapolation step over time because we assume that the weights are optimal. We don't allow the weights to change. Okay, and this is a very strong restriction, this extrapolation step over time, because that's what we need for our counterfactual. In contrast, the changes in changes estimator estimates the change of the distribution over time in the univariate case, and then applies it to the control group over time. So the changes in changes estimator needs this classical order preserving property of having a function h that is strictly increasing and continuous in U. And what I will need is an essentially linear function. So I need a function that preserves the optimal weights. And something that preserves the optimal weights is mathematically called an isometry. And you can show that this is actually a linear, almost affine linear function, essentially. Because the weights need to be optimal, which means that all of the shapes need to be optimal. And linear functions provide that. And what I need essentially is like a linear function in my Wasserstein space. Okay, so that was the idea. And now I'm essentially done.
Okay, thanks, Florian. That was a very interesting talk. So let's switch to the discussant, Kaspar Wüthrich.
Yep, let me share my slides. Can you see my slides?
Yes.
Okay, great. So, thanks a lot for giving me the opportunity to discuss this very interesting paper, and thanks to Florian for an excellent and quite exciting talk. So overall, I thought that this was an impressive and super interesting paper. Put it in the words of Alberto, that this is really very cool. And what I really liked about it, beyond the fact that I liked the paper, is the fact that it suggests so many directions for future research. It really pushes the boundary of how we should think about, generalizing this simple and intuitive, appealing synthetic control idea to more general spaces, basically. And so very quickly, in terms of a summary, I think Florian did an excellent job explaining the method, so I'll go quick about this. So the idea is that classical synthetic controls focused on aggregate outcomes and basically approximates the unobserved counterfactual as a weighted average of contemporaneous control outcomes, where the weights are obtained based on the pre-treatment period. In a simple case where you don't have additional predictors, you just run a constrained regressions with the adding up and non-negativity, so the simplex constraints. So this paper, what it does is basically says, well, let's take inspiration from this idea and say, suppose I want to approximate the whole distribution of the treated unit in the absence of the treatment. And I want to do that using a weighted average, a suitable weighted average of contemporaneous control distributions, where the weights are also obtained in the pre-treatment period. So I put weighted average here in quotation marks, because as Florian discussed, defining a weighted average here is far from trivial. And I do believe that one of the key contributions of the paper is actually to come up with a suitable notion in this more abstract space of probability distributions. Interestingly enough, the resulting method is essentially a changes in changes extension, an extension of changes in changes to synthetic controls in particular. And I think there's a deep connection there using optimal transport, and in a one-dimensional case having these quantile maps and the changes in changes idea. And this is exactly what comes out of this model, which I thought was quite exciting from an intellectual connection perspective. I would like to structure my short discussion around the 4 challenges that I see when one tries to extend the classical synthetic control idea to distributions. And so really the first challenge, as I already alluded to before, is defining a suitable notion of a weighted average. A natural approach, which I would have thought about, I think I actually did at some point even think about that because I was working on quantiles a lot. And so I just thought, well, let's just take this mixture approach here, or potentially a quantile version. This version has actually been developed in this recent paper by Chen in the Journal of Applied Econometrics. This is something that is easy to interpret. That's probably also why I thought about this in the first place. But as Florian shows, it has issues. And in particular, it's not geometrically faithful, by which Florian means that it basically doesn't allow you to approximate general nonlinearities of the target. And the solution that the paper proposes is to use these barycenters in 2 Wasserstein space. So here I have the definition of a barycenter, which Florian explained at length. Let me flag the one feature I think that really makes this approach work, which is the fact that this works with the Wasserstein distance, or is defined in terms of the Wasserstein distance. And the Wasserstein distance, different from the kind of naive approach by just trying to minimize the distance between this law and this mixture here, it operates on the underlying supports, not on the distributions. And so that implies that you have this geometrical faithfulness, that you can basically approximate that circle based on the 4 boxes, which you cannot do in the mixture approach. I had 2 main comments on this approach. First of all, I would find it really exciting to try to further formalize and empirically motivate this notion of geometric faithfulness. In particular, from an empirical perspective, I would like to better understand when we do want something that is geometrically faithful and when we do not want that. In particular, this relates to the discussion interpolation versus extrapolation that is a very traditional discussion in synthetic control literature. And here is much more exciting in the sense that with distributions, you can be interpolating, so you can still be within the simplex, having simplex weights, and nevertheless be extrapolating beyond the supports of the control distributions. And then extrapolation would even be one step further, where you go beyond the hull of those distributions. And so it would be really interesting to see, in applications, how this works out and, what this approach brings to the table. And I do believe, that distributional outcomes are of interest in so many contexts that, that is a very exciting direction. The second challenge is estimation and computational feasibility. And I think this is one of the main contributions of the paper, and a very elegant one. So the observation is that the natural approach that you would have chosen once you've decided that the barycenter in 2 Wasserstein space is an appropriate notion is basically this one here. And as Florian discussed, this computation of the weights here is a bi-level optimization problem that is very difficult to solve. And so what he proposes is to use this connection to optimal transportation to come up with this formulation here. So basically working with this tangent space. And this here, this nabla phi t, this is a vector of optimal transportation maps. And the cool thing about this is that this is essentially a regression. It's a tensor variate regression that admits a unique solution and is easy to compute in practice. A sufficient condition for the applicability of this procedure is that the target is absolutely continuous, but as we've seen, it also works in some cases with discrete distributions. I'm not too worried about this because I personally think that the method is most interesting when you have these continuous distributions. That's where quantile regression, those classical approaches are also typically applied. I found this reformation very elegant and practical, as I said. What the paper currently doesn't explore, and I've discussed that with Florian when he presented at the paper at UCSD, and after that a bit, is the fact that this only works when the optimal transport is achieved by functions. And in general, this may not be the case. And that would then lead potentially to partial identification, which creates an exciting new set of challenges in terms of identification, estimation, and certainly also inference. And that area is kind of unexplored. I'm not too worried, as I said, because I think the absolutely continuous case is one of the leading cases that we really care about this, but that would be exciting, potentially for another paper. The third challenge is identification. And so by identification here, I mean trying to justify the procedure that we have just seen, which generalizes this intuitive idea of synthetic control to the distributional space based on an underlying model of the potential outcomes. And this kind of exercise actually has a long tradition in the synthetic control literature, going back at least to Alberto Abadie and co-authors 2010 JASA paper, where they try to use a factor model to better understand synthetic control. So Florian does something similar here. He takes the production function model of Abadie and Imbens and tries to understand what condition he needs to impose on this production function that you have here, so this non-separable function of t and unobservables u, in order for the approach to be justified. And it turns out that a sufficient condition for this to work is that this h function is a scaled isometry in two Wasserstein space. And so here I have the definition of a scaled isometry in the general spaces, and you can see that in the Euclidean space, this is basically parameterized by rotation shifts and reflections, essentially affine maps. The paper then talks about two Wasserstein spaces and isometries in two Wasserstein spaces, and there is this paper in the math literature that has results characterizing those isometries. And the conclusion of the paper is, those are almost the same as their Euclidean counterparts. I thought that this was an extremely useful result, but also a somewhat high-level result. And so I personally view this as a starting point. And I was wondering whether there are easy to interpret necessary and sufficient condition for H to be a scaled isometry. And I'm particularly curious about that because such slightly more primitive conditions will potentially allow us to connect to the identification literature in non-separable panel data. And I think that would be a really exciting connection to exploit, also in view of the similarities to the changes in changes approach. And also, in the end, also because I'm not used to thinking in terms of Wasserstein spaces. And so, if I have to think about an isometry in those spaces, that is not as intuitive to me as it was, in the Euclidean space. The fourth challenge is inference. And so currently the paper suggests using the permutation approach that is very popular in the synthetic control literature, which can also be applied here. This approach relies on random assignment. And if random assignment fails, which is often the case in these aggregate panel data settings, one has to interpret this approach slightly more qualitatively. And Alberto has an excellent discussion on this in his recent review. What this motivates, in my view, is just a search for complementary approaches that rely on other sets of assumptions that may be more credible in some applications, less credible in others. One such approach is conformal inference, something that I've worked on with Viktor Chernosakov and Yingxu Xu. And this is really a sampling-based approach that relies on permuting residuals over time in the case of aggregate outcomes. So what I particularly liked about the approach, and which is why I'm mentioning it, is that this is an approach that does not rely on characterizing asymptotic distribution theory of complicated estimators. It just requires consistent estimation. And Florian actually already has consistency results in his paper. Moreover, the underlying idea, the synthetic, this conformal inference method has been extended to more general spaces, in particular to functional data settings. So I was wondering whether there would be a cheap way to come up with an alternative inference procedures by just combining the ideas in the paper that we have on synthetic control and conformal prediction, and this paper by Lei and co-authors. One could certainly also go for asymptotic inference results because there are closed-form solutions available in the one-dimensional case. One could use plug-in estimators and try to see whether those compositions of functions are differentiable. And then finally, the paper mentions in several instances that there are testable restrictions, and so that naturally, poses the question whether one can develop practical specification tests. So to conclude my discussion, I'd like to mention 3 points that are not directly related to these 4 challenges that I discussed. And the first one is also going back to Jesse's question. I'd really like to see that method in action. And I do remember that an earlier version of the paper actually had a short empirical application, if I am correct. And so the application, I think, was minimum wage, or at least the paper currently mentions minimum wage. And I do believe that this would be an exciting application. In the minimum wage debate, at least as far as I'm concerned, I do care about distributional outcomes like inequality. And it's also a very difficult empirical problem. And so having a flexible approach for approximating counterfactuals, that may be exactly what we need. And so, I'd be really interested to see how this would play out. The second question or comment I had is that in the context of the changes in changes model, one thing that one can do in order to incorporate covariates is to work with conditional distributions. So basically first estimate conditional distributions and then apply changes in changes. And I was wondering whether one could do something like this here as well, instead of just stacking the covariates together with the outcome variables, which is currently how covariates are incorporated in the paper. And then finally, I was wondering about the connection to functional time series analysis, in particular functional time series analysis with co-integration. And so Brandon Baer and Wonky So have a series of papers on characterizing co-integration in abstract spaces. I was wondering whether there is a connection here between the approach here and the approach in this very different literature. That's all I have in terms of my discussion. Thanks again for having me. Thanks to Florian for writing such an exciting paper. I did learn a lot, and it really has me thinking about where we could go with this. So that was great.
Thanks, Kaspar, for a very interesting discussion there. Florian, you want to respond to any of the thanks, or you want me to open it up for a general discussion?
Just like one second, yeah. Kaspar, that was wonderful. Thank you so much. These are all very important points. Some of which I try to deal with in the first version of this paper that made everything a little complicated. And now I think I've broken it down in the most simple way. But I'm in particular, I'm very excited about the conformal inference for this, for sure. The primitive conditions for identification and the co-integration part could also be very, very useful. And as I said, there's many ways in which one could also generalize the mathematical theory, and there's also mathematical questions that have not been answered so far. And I'm currently also working on some of those. And again, thank you for letting me present this work in progress here.
All right, great. So first, do any of the panelists have any questions? Or should I? There's a couple of questions from the audience, so I do want to get to those. So Andre Strakar had a question. Andre, you want to? Oh, sorry, Davide.
Yeah, I had a quick question. Sorry to interrupt. So something interesting that you may also consider is the fact that here you're not exploiting changes in time. So this is a nice connection that you do with the changes in changes. So it would be nice to see if you can construct an estimator that may exploit the isometries that are either of the control unit over two periods instead of isometries of the treated with respect to the control units, and vice versa, construct weights that are in the same spirit of the synthetic control of the distributional synthetic control, and try to be robust to either of these isometries. Do you think that may be possible or not?
I think I understand what you mean, and if I do understand what you mean, then that's a very good point. So you actually mean that I don't need to just do it like time point by time point, but I can allow for some dynamics in both groups and try to match the groups over specific times. Yes, I can. It will become higher dimensional. So the actual issue here is the computational part, which again, over the last year, very famous mathematicians have come up with ways of estimating these transport maps and so on pretty efficiently. But there's a lot of machinery involved, right? We need consistency for those, and I think the only current restrictions for this is the computational part. But theoretically, that's where I would actually like to go, right? You have like several time periods, and you match the whole time period. And yeah, exactly what I want.
Sorry. Yeah, exactly. If you can exploit also the time dimension, that would be nice.
Exactly. Yeah. That's a great point. Thank you. Yeah.
All right, Andre, you want to ask your question?
Okay, thanks a lot for allowing me to ask this. Basically, one thing that is unclear, it was really great presentation and actually the extension to distributional data, I would say, but is this really, I mean, connections here, you have distributional data, functional data, that's why I was also asking about the discrete distributions. What you're exploring, I think, relates to empirical distributions. And in this case, it would be interesting, there are regressions, not in causal inference, but some of the regression machinery works a little bit differently, like quantile models that Kaspar Wüthrich was explaining. You have two component models. Maybe also this could be additionally included in the model, if I have right what I observed.
Okay, thank you. Thank you for this question. I'm not quite sure I understand, because this idea works fully theoretically in the population for continuous things. And the implementation then, if you want to do this in practice, you use empirical distributions. And I show that, you know, when you use empirical distributions to estimate these things, you get something that converges, that is consistent to your weights and to your counterfactual, essentially. What is true is that, I don't know if this answers the question, but what is true is that this idea is currently a regression on outcomes, meaning that I have distributions with the same support. What I want to do, and this is also something I'm currently working on with some mathematical co-authors or some co-authors from the math department, is to allow for something that is an actual generalization of a linear regression in this Wasserstein setting. And that would allow, that would require that we predict a distribution on a specific support by controlled distributions that might have many completely different supports. Okay, so predicting a one-dimensional distribution by having, you know, multi-dimensional distributions or so on. That would be like a purely theoretical idea, but that would give you a generalization of linear regression. And this has been useful apparently, or people are looking for generalizations of linear regressions, in particular in the genetics literature, where they try to predict and extrapolate over specific genes and so on. This is what I have heard so far. But to answer your question again, I'm not constrained to just empirical distributions. For implementation, yes, but the whole thing is actually a theoretical abstract approach.
Thanks. Maybe just shortly to add, it would possibly be interesting to look into this literature to see how also this regression machinery additionally works. It constructs to symmetric quantiles and so on. I'm sorry for taking the place. Thank you.
Oh, okay. Okay, thank you. Thank you.
Thanks. There's also a question from Igor Kaifetz. Igor, you want to ask your question?
Yeah, thank you, Guido. So I also trying to understand this extrapolation thing. So if nearby states, near California, suppose we don't have data on rich households there, and then somehow your method allows us to try synthetic control for these families and then to compare to Californian rich households. So is it a good thing to do it all? And this kind of extrapolation is based on like purely mathematical notion of these Bayes centers. So what's the kind of economic mechanism which says us that we can do this comparison? For example, when we consider regression, we assume that relationship is stable. When we do synthetic control classical approach, we assume that averages are stable. What is assumed here really?
That's a great question. Thank you. Just to preface this, I usually, in principle, yes, I can impute the distribution or parts of the distribution of my target if that wasn't there. But essentially, what I need, I want to replicate the whole distribution. So what I need is that my target is a distribution and has all the observations everywhere. So I have a functional relation that I want to replicate. So I do not actually impute new parts in the distribution. I just try to replicate the distribution. And this notion of extrapolation and interpolation is more of the notion of the classical synthetic controls method. When I talk about interpolation, I actually only look at the information essentially I have from my donor distributions. And as you could see in this one example I had, sometimes my control distributions or my donor distributions are too far away from what I want to replicate. And in that case, they don't really have economic meaning at all. And they're not good control distributions. For instance, if I try to look at California, and then I have other states where you have completely different distributions and completely different outcomes, then those are probably bad control distributions. When I talk about extrapolation, I mean that I can better replicate with the information of my bad control distributions. I can still try to replicate my actual target, and I can do that better. So I'm not imputing something new in my target. Extrapolation just allows me to linearly, and this is also a partial answer to your question, allows me to linearly extrapolate over distributions. So as in the classical linear regression case, where you make the linearity assumption that is obviously useful for many economic settings, I now have linearity in distributions. So I have my distributions in the univariate case essentially, and then I have when I extrapolate, I use what I have, the information that I have, and I claim that for negative weights, everything stays the same. So instead of just having linearity in points, I have linearity in distributions, and the economic implications of that are actually exactly the same. And the point of extrapolation is to not impute something new, but to just use my information in a different way to replicate what I want to replicate better. And for this, I need that the supports of my control distributions are larger than my target so that I can replicate everything. And that has a very similar flavor to having the classical average treatment effect literature, where you have the overlap condition. So that has a very similar flavor, but only in the extrapolation case. I hope that answers the question.
May I ask something related to that? Is how do you, in practice, how do you use all those notions that you just explained to, if I have to choose the donor pool, as we often do? This related to the previous question.
That's a very good point. So I currently, I had an application at some point, and I just used all the states available. I know there is a lot of cherry picking you can do by choosing different weights or a different set of donor distribution. I have to say this is a great question. I don't know how to deal with this currently because the other question, I think Alberto, you asked me that too. How to check if my approach actually replicates it well? I think those two things go hand in hand. So if I get like a nice test where I say, okay, I can replicate this well, then this will also tell me what type of set of donor distributions is a good type of set, and that is something that is that is very useful.
With a caveat, right? That you can have something that replicates very well, but they are at the same time very far away from the target distribution. Kind of they cover everything, but they are far away, right? And that you are doing quite a lot of interpolation.
Yes, I'm doing quite a lot of extrapolation. If you want to do extrapolation, you can. And I just wanted to show this because extrapolation in this functional setting is not as robust. So interpolation, and it shows. Interpolation is very, very robust and it works fantastically well. But I'm essentially only using the information that is there in like Colorado, Nebraska, and so on. I'm not trying to to just find something that isn't there. And when you do extrapolation, then you get into this problem. Like, what does it mean to have a weight of minus 0.9 for Colorado? I don't know. But that is a more fundamental question, actually. Yes.
But even in interpolation, right? Imagine that you have these 4 squares, but then you have more squares in the outside. Perhaps you want to just retain only the inner squares and forget about the other ones. And like, is there a principal way to do this? But anyway, like.
Oh, that's a good point. So the more the better. So my current state of knowledge of this thing is the more you have, the better, because the better you can replicate your distribution. So I would recommend everything that makes economic sense. Everything that makes economic sense should be used. But again, what is economic sense? It's like legal speak, actually. But I would, as you can see with my distributions, where I had these like hundreds of controlled distributions, I did a better job than with just 4. So you should use 100, and some of those will get zeros. So I also observe sparsity for some reason, and I don't quite understand why, in the interpolation case, very, very similar to what you have in your classical method. But yeah, the more the better, actually. But that's all I can say. I have not thought about this more.
All right, thanks very much. It's exactly 10:30 here. So let me thank the speaker, Florian, the discussant, Kaspar, and the panelists, as well as the audience. That was a great talk, great discussion, very interesting questions. Thanks, everybody. And so in 2 weeks, Friday, March 26th, we'll have Vera Semenova from Berkeley talking about better lead bounds, as in David Lee. So looking forward to that. And I hope to see everybody there next time. Thanks.